Good Friday to you, everybody in GOV 603. Welcome to week, boom, bam. I just went bigger. 11, week 11. How's everybody doing? How you hanging in there? We're past modular week or spring break week or whatever you want to call it. Now we're coming around the back stretch of the semester, so hang in there and hold tight and do what I do. Say, delicious, stay sufficiently caffeinated. What do we have here today? Short wave coffee, one of my favorite little coffee shops in the town that I live in. That's much better. Now, you're sufficiently caffeinated instructor. Let's take a look at this week, and let's take a look back at the questions and your answers from last week. Going forward, from this point forward in the semester, the thing you should be focusing on is your paper. Now, I'm in my office Monday, Wednesday, Friday from noon to 2 Eastern Daylight Time. If you want to call up and go over your paper with me, a lot of you have, which is great. But remember what you're doing. You are writing a proposal. So imagine you were writing to me for a grant to carry out a bit of research, okay? So first you'd want to, tell me what the problem is, what it is that you want to research. Why is it worth the time and the effort? Give me a little bit of give me some background, not a little bit of background. That's your literature review. What have others studied about this problem? Set the stage. What's the backdrop? What are the big picture items that we need to understand in order to do this research? And then tell me how you would go about researching the topic if you were given money to do so. So what's your hypothesis? Remember, a hypothesis has three parts, all right? It has at least two variables. You make a prediction about the relationship between one variable and another, and that prediction has a direction. It flows in one way. So you would tell me what sort of study you would undertake or design to gather data to answer that hypothesis or the research question. You don't have to do it. You just have to, tell me what you would do if you did do it. Sort of think of it like this way. You're the O.J. Simpson of semester research papers. If I were gonna do the research project, this is what I would do. And then you tell me a little bit about, what would be the significance if the hypothesis were supported, if it were not, and what would we do with that information? Okay, that's what you're up to. If you have any questions about where you're at or comments that I've made, you're unsure, call me during my office hours. We will get you straightened out. I guarantee it. Okay. Last week, week 10, we started with some, almost out here too. We took a look at regression analysis and had a little bit of discussion to help you distinguish between causation and correlation. And remember, this is really important in quantitative research, that correlation does not equal causation. That is, just because two things happen simultaneous to each other doesn't mean the one thing is causing the other. So, there's an example. You could take a survey of the number of ice cream cones sold during the months of the year and look at the months in which the greatest number of ice cream cones were sold. And then you could look at the data and look at drowning rates in public pools, God forbid, and see in which months there was the highest number of people who drowned in public pools. So having that information, you probably would find something like the greatest number of ice cream cones are sold during the summertime, right? Well, so let's say July, August. Okay, the greatest number of ice cream cones are sold July, August. But it also happens that the greatest number of drownings in public pools happen in July, August. Could you conclude, therefore, that ice cream cones cause drowning? No, you could not. Because although that's correlation, high number of ice cream cones sold, high number of drownings, that's not causation, ice cream cones causing drownings. That's what a regression analysis is for, is to establish causation. All right. And, maybe one of the better ways, easier ways, quicker ways to go about it is for you to actually do a little regression analysis. And so that's what we did last week. In the assignment folder, I gave you an article that I wrote. I write for a number of places, and one of them is a national newspaper. And this is an adaptation of an article that I wrote for the newspaper, in which I took a look at a study that was done. It included 1.4 million people. And what the researchers did is they simply looked at, most of the people were drawn from the state of New York. They looked at the hospital records. That's it. They didn't interview anybody. They just looked at hospital records. And they said, okay, the people who are coming in at age this, and this, who have at least 2 of the 4 most common comorbidities. And, when you check into a hospital or go to a quick care or something, they ask you this long list of, what conditions do you have? And you check the box. They took that data and then they looked at what happened to them. Now, these are people, we should say were coming because they had COVID-19. So were they admitted to the hospital? Were they put in the ICU? Were they put on a ventilator? Or did they die? And those 4 things qualify as severe outcomes. So they put this table together and they said, so between, pick an age group between, 18 and 29. This was the percentage of people that ended up in hospital, and this was the percentage of people that ended up on ventilators or in the ICU on ventilators and died, who had no comorbidities, 1 comorbidity, 2 comorbidities. Now, the 4 most common comorbidities are diabetes, cardiovascular disease, obstructive pulmonary disease, COPD, and renal disease, which is driven by diabetes. Now, there are 2 kinds of diabetes, type 1 and type 2, and it's a terrible disease to have, all right? And type 1 diabetes is genetic. You have it, you have it. Type 2 diabetes is developmental. That is, it develops in life and usually develops about 90-something% of the time because of what's called insulin resistance. The person has had a life history of taking in a lot of sugars and a lot of carbohydrates, and it's caused constant and massive secretion of insulin, and the cells just don't respond to it anymore. That is, they're resistant, and this leads to diabetes. All right, now, you may be asking when they did the study, well, why did they only look at 0, 1, and 2 comorbidities? Because what they found was the percentage of severe outcome didn't change that much from 2 to 3 to 4 comorbidities, so they just cut it off. So they just said, okay, at 2. Now, they've given us these ages, they've given us these number of comorbidities, and they've given us the percentages of those people who had 0, 1, or 2 that ended up with these severe outcomes. Does that in itself show causation? No. It shows correlation. But that's why you use a regression equation. And that little bit of software had the mathematical equation behind it, so you don't have to work the math. That's why you use a regression analysis, a regression equation, to establish causation. So I asked you to take a look at that. I asked you to select, the age ranges of your choice and crank out your answers, okay? Let's see what you did, and then we'll draw, maybe a little lesson and sort of a little explanation of, okay, what's the point? So Edward, taking a look at yours, and then, I'm sorry, and most importantly in doing it, not just plugging the numbers in and clicking the button, I asked you to tell me what does R and R squared stand for? What does that tell us, okay? So Edward, the coefficient R is a statistical value that tells the strength and direction of the relationship. Okay, so what that means is, because R can be positive or negative. So if it's positive, that means there is a relationship from this variable, person of a certain age with a certain number of comorbidities, leading to severe outcome. It has a positive relationship. Now, could it go the other way in this case? Maybe. Could it be that those who had severe outcomes from COVID-19 develop these comorbidities? Yeah, maybe. I mean, practically speaking, no, but in a scenario it could. But since the number is a positive number, it tells you that it's going in that direction, okay? So that's exactly right, Edward. Okay. And then so here we go. Strength and direction relationship expressed as a positive or negative number between 0, 1 and 1. R for the first age group that you picked, Edward, 19 to 21, R is 0.9255. Okay, so when we do the math, we work in decimal points, but to translate that back into percentages, you just times it by 100, so you move the decimal over. So 92% of the strength that is, the relationship between here and here, 92% of it is caused by the first thing. Okay, so that's what the R tells you. So there is a very strong relationship between comorbidities and severe COVID outcome, two comorbidities. Because I asked you to create that scatter plot, that graph. And if you look down on the x-axis, you can look at where the line intersects with no comorbidity, one comorbidity, two comorbidities. Okay. All right. And okay. And then you pick the two age groups, 18 to 29 and 30 to 39. And for 30 to 39, R equals 0.9482. These R values show the correlation between comorbidities and death rates. R squared value is a statistical measure that indicates how much variation of the dependent variable is explained by the independent variable. That's exactly right. Let's put that into English. So what percentage of the severe outcome is being caused, remember we're looking for causation, caused by the number of comorbidities. Now in your case, Edward, you looked at 18 to 29 and R squared equaled 0.8565. We just round that up and we say 86%. And then for age group 30 through 39, 0.899, round that up, that's 90% R squared. So what that means is 90% of the bad stuff that happened to this person that had COVID-19 is directly caused by their comorbidity, as opposed to someone who didn't have any comorbidities. And then when you print out that scatter plot graph, you only get two dots on that three dots, on that scatter plot, because you only have three things: 0 comorbidity, 1 comorbidity, 2 comorbidities. But if you had more, you'd see those dots all together. And what you're looking for to establish a pattern is that they're all clumped around that line, that slanty red line. All right. So if you look at the scatter plot and you look at, say, ages 30 to 39, we'll just take that group from you, Edward. You way over on the 0 comorbidity, the percentage, and this case where you're going to use death rate with 0 comorbidity is just slightly over 2.5%. However, you add in 2 comorbidities and that death rate goes up to almost 9%. Okay, that is a statistically significant jump, and you could point to that and say, "Bam, that's causation." Okay, so that's why we're doing this. And some of you, sort of chimed in. Judah, I like what you had to say. This is a response that you made to Mary. Mary, comparing the successive age groups is a good choice for your assignment. It allows for examining whether or not there are incremental changes in ICU rates as people get older. The fact that 70 to 79% age group has an R of 0.99994, which is like almost 100%, is crazy to me. In order to get anything less than 1, R has to be calculated out to 4 significant figures. That is about as close to perfect as 1 as I think you can get. And you're right. That's if we rounded that up, that's like 100%. 100% the relationship is there. Okay. So the question is, why did I pick this particular exercise to run regression analysis? Well, number one, the data from this table is pretty straightforward and easy to deal with and plug into a regression calculator. And by the way, you can buy software suites that have regression calculators in them. You can get them off the internet like this. These are not hard to find by way of little software engines. Okay. So this one, the numbers were easy to plug in and then to get something out. Okay. And by the way, I did not select this. I mean, I wrote an article about this, but I did not select this particular data set and give you the article to say, "Hey, America, you're too fat and you're out of shape, and therefore you have diabetes." Okay, there's no finger pointing in this exercise. That wasn't the point. Okay, I mean, I will tell you that at my present state, I myself, I'm about pretty close to, maybe even slightly over 20 pounds heavier than I ought to be, and I am successfully losing that weight, but it is not easy. It is not easy. Okay. And by the way, you read a lot about how to calculate a healthy body weight, body mass index, BMI. I'll tell you, one of the simplest ways, to determine good body mass, really straightforward. Take a piece of string, stand on the very tip of it, put it, just a little teeny bit of it, just enough to hold it down under your foot. Stretch it up, hold it on top of your head, pinch that with your fingers, and then cut it off right there. Now you have a length of string. Take that length of string and fold it in half, and then hold it. So now you have a piece of string folded in half, and wrap that around your waist. If you can touch the ends of the now folded in half string, the one side has the two ends and then the other side has the loop. If those can touch, that's a good body weight ratio. And that's not a perfect measure, but it's much easier than the body mass index calculations, which don't take into account a lot of other things. Now, why is that? Because visceral fat that's carried around the middle is perhaps the most harmful to the overall system, especially your cardiovascular system, and is one of the indicators of the onsets of these other comorbidities. Okay, so just by the way, as long as we're talking about body mass and as it's related to comorbidities. Okay, but why did I give you this? Well, I wanted to give you an exercise not only that was straightforward by way of regression, but something that was tied to a political question that would be very familiar to all of you. And I think this is. I mean, this is politics. It would be an interesting study, a political study would be to compare the real causes for severe COVID outcomes, like using this table that's very data rich. It's 1.4 people. Compare the causes for severe COVID outcome with the information that was propagated by government entities, NIH, CDC, health entities, and the media. Was there any discrepancy there? Because we were told by many, many sources, including those in our government, that the COVID-19 pandemic was a pandemic of the unvaccinated. But the health system, hospitals, clinics, and so on and so forth, they only incur a cost due to public illness when the ill show up at the health facility. So if you get a cold, and a coronavirus is a respiratory virus. They're very common as the viruses have been around for a long time. If you get a cold, you feel lousy, you don't go to work, or you take time off from school. Okay, that's one thing. But if you get a cold and you have an existing comorbidity, and the percentage of severe outcome, the lowest threshold meaning I got to go to the hospital, goes up by like 900%. Okay. That, from staying home to going to the hospital climbs by 900% with one or two comorbidities. That's a significant driver of the pandemic and the strain that it puts on the health system and the resources and the government funds. And that should drive policy. So I gave this to you because, one, I knew you would be familiar with it. And two, these kinds of questions and the use of this sort of data is exactly what should be going on when making questions about, say, whether to shut down businesses within a city, whether to require people to wear masks, whether to pump money into a vaccination program, and whether to, decide, well, lucky we're over that COVID-19. We'll never expect to see another coronavirus again, and there won't be a COVID 2020 or two. I guess I just call it 24 or 23. It may not be a coronavirus, but these viruses will be back because they're tough little buggers. And politically speaking, if we're not addressing the root cause of the problem, then around and around we go. So that's why I used this data. There was no finger wagging that was intended here. This is a very real political question, and one of the ways, regression analysis, that you can get at answering are we addressing the right thing in terms of what's causing the problem within our political system. Okay. All right. I hope you enjoyed the exercise. You get to sort of put into practice some of the theoretical stuff that you've been learning. All right, question number 2. When might a researcher use a correlation analysis? Explain your answer. Find a link to an online correlation analysis. Okay, Judah, since we got your feedback, let's grab you. According to Cavello, correlation is used for a quick and simple summary of direction and strength of a relationship between 2 or more numeric variables. Addition of correlation analysis, and here's the important part, cannot be used to determine causality. So it's use a correlation analysis when you have a hunch that things are connected. First of all, use a correlation analysis to see if they are actually happening at the same time. So that's a way to confirm your hunch. But then go one step further to confirm your hunch about causation, and you've got to do something else. Okay, so that is regression. Based on this information, a researcher is most likely to use correlation as an initial quick data analysis to get an overview of their data before going into in-depth calculations, which allow for evaluating causality. Excellent, excellent answer, Judah. Right on the money. Okay. Question number 3. When might a researcher use a regression analysis? Find a link. Okay. Andrew. Regression analysis in simple linear terms. A researcher would use regression analysis to predict the relationship between 2 variables, x and y, via a created, let me just stop you right there, though. Not 2 variables, x and y, 2 variables on an x and y axis. Make sure everybody understands that, okay? Because you could have more than 2 variables. So in the case of the data that you did, you in fact had 2 variables, 2 independent variables, and 1 dependent variable. 2 independent variables, meaning age, comorbidity. Okay, and then the dependent variable, severe outcome. So important. You're right. You're in the neighborhood, Andrew. But that's an important distinction, everyone. Via a created model or equation to estimate the random variable value z. All right, and that's the outcome. And this is from Cavello. It would determine a detailed cause and effect relationship between quantitative variables that are not always in the same direction to create a prediction of an unknown random variable. This analysis explains how x causes a change in y, or y to x, whichever way you want to look at it, to make a prediction z. That is the outcome, right? And z, although you're looking, the number that's generated is r. You can R stands for regression. That becomes that relationship, that percentile relationship of direction and causation. That's your z value. Okay. And then I gave you, we have some letters here, Andrew, which is perfect. A refers to the y-intercept value of y when x is 0. B refers to the slope, rise over run, y equals a plus b times x, predicted formula. Okay, the prediction formula. And that's basically, that little equation is what the regression calculator is running for you behind the scenes when you put the numbers in. Okay, good. Number 4, summarize and explain the difference between correlation and regression. Mary, I like what you did here. Correlation shows the relationship between the variables, but regression shows how one variable affects the other, right? You just got to bang this into your head because you will see it again. Final exam, a wink. That correlation shows that there's a relationship, but it doesn't tell you causation, doesn't tell you direction, okay? It doesn't tell you strength. You've got to have regression for that. In correlation, the variables move together, but in regression, there is clearly a cause and effect. And that's a good way to put it. Back to the ice cream analogy. In correlation, the number of ice cream cones that are sold in the summer goes up, and the number of drownings that happen in the year, and ice cream cones during the year goes up in the summer, and the number of drownings that happen go up in the summer. The numbers move together, but the one isn't necessarily driving the other. Okay, that's an excellent way to put it. And for that, you need regression. Okay, all right, everybody. Good job. Send me some feedback. Did you enjoy the regression analysis exercise? Was there anything that you found that surprised you about running that and running the data? That is, did you learn anything? Did you go, I had no idea. I didn't even know what comorbidity was. Maybe that's something that you learned. Let me know. Okay, send me an email. Let me know. And again, I apologize for the delay in this video. It's been a bumpy week, a lot of sickness in the house, including me, but I think everybody is on the mend. No severe outcomes predicted here. May it please God. So remember, keep working on your papers. And, for those of you that have been having some difficulty, thank you for reaching me. And some of you have been having some, really tough events in your life. And I have you in mind and I'm praying for you. I think about all of you frequently. So, have a great weekend and I will see you on Blackboard. Bye-bye.